Here we will set up transfer equation. First, let us imagine we have an infinite small element. And the global position of that small element is represented by the vector of r. And the direction of energy change we are interested in is omega hat. To construct the model, we define the energy radiance L, which is the energy flowing per unit time through an area per solid angle. So the unit of L is watts per centimeter square per steradian. So the transfer equation describes that the change in L at the position r at the angle of omega hat at time t, the changing rate of r at the time t is being driven by 4 parts of the energy changes when the photon comes into the tissue element. The first one is when the photon comes into the tissue at the direction of omega hat prime, and it is being scattered to the direction of omega hat. Since the omega hat prime can be any directions, so we need to integral over all possible directions of omega hat prime. But not all the photons will be scattered into the direction of omega hat, so here we need a function of f, which represents the statistical possibility rate of how likely they are scattered into direction omega hat. Times the energy we have coming in the direction of omega hat prime. Then we times mu s, which is the scattering coefficient. Since the scattering coefficient mu s is defined as the proportion of photons being scattered per unit length, so we need to times the speed of light v in the tissue to keep the unit on the right-hand side the same to the unit on the left-hand side. We will divide v for each term in this equation, so that will be 1 over v on the left-hand side. The second one is when we have a source S in the element, the source is adding more energy directly, so we just add the term S on the right-hand side. The third one is the gradient of the energy L itself, which is also driving the changes of the energy. We can think of it as a drop of ink in the water, and the ink can be driven to diffuse in the water by the gradient of itself, since the gradient is toward to the higher energy part from the lower energy part, but the ink is driven to change in the opposite direction. So we need a negative sign here. And we are only interested in the direction of omega hat. The fourth one is when photon comes into the tissue at the direction of omega hat, but it is being scattered to some other directions. That will be causing a loss of energy, so we have a negative sign here. And that part of energy loss could be represented by scattering coefficient mu s times the energy rate of L. The last part is when the photon comes into the tissue at the direction of omega hat, but it is being absorbed, never comes out. So that is also a loss of energy. So here's Manor's sign, and that part is represented by mu A times L. So mu A is the absorption coefficient. So this is basically the transport equation. We then simplify it a bit by defining mu T transport coefficient, which equals to mu S plus mu A. And then we also move the negative part on the right-hand side to the left-hand side. So we have simplified it as 1 over V, derivative of L over T, plus gradient of L times omega hat, plus mu T times L equals to mu S times integral over L omega hat prime times F omega hat prime over D omega hat prime plus S. So this is basically the transport equation. That is our first equation. So we will derive the diffusion equation from this transport equation, and at the end we will derive y equals to A times